Hello, this video shares with you a recent research work by the Wireless Communication Research Group led by Professor Z.Gao from Beijing Institute of Technology, grant-free NOMA-OTFS paradigm, enabling efficient ubiquitous access for LEO satellite Internet of Things. This research work have been published on the IEEE TWC and IEEE network, respectively. The paper link can be found below the video. You are welcome to contact with us through email and the research group's website. This video briefly introduces our work from 4 aspects. First, let us introduce the research background. The next generation wireless communication is facing a large-scale access demand for seamless global coverage. As an important component of the space-air-ground-sea integrated networks, low Earth orbit satellites have been regarded as a promising enabler to complement terrestrial wireless networks in providing ubiquitous connectivity and bridging the ever-growing digital divide in the expected next-generation wireless communications. However, there exist numerous challenges in the large-scale connectivity of Internet of Things assisted by LEO satellites. First, the number of IoT devices is massive, and they are dominated by uplink services. The second difference is that unlike terrestrial cellular networks, the terrestrial satellite link is long and the caused propagation delay is high. The third is that the high-speed motion of the LEO satellite leads to a significant Doppler effect. These challenges pose higher requirements for multiple access schemes and signal processing algorithms design. A paradigm shift in multiple access methodology is indispensable to realize efficient ubiquitous access for LEO-SATS in practice. The grant-based random access protocol-based schemes dominate the existing cellular network standards nowadays, for example, LTE, LTE-A, 5G, NR and NB-IoT. This protocol stipulates active entities initialize the access procedures through a physical random access channel in a contention-based manner to set up the connection with the base station. After the typical 4-step handshake procedure is completed, the connected terminals are allowed to initiate a grant application request for transmitting their payload data to the base station on allocated resource blocks. However, the solutions developed for terrestrial cellular networks are not directly applicable to LEO satellite systems. First, the access latency caused by standard handshakes and grant requests may far exceed the round-trip latency of the link and constitutes the main latency source. Second, the scheduling signaling overheads are prone to exceed the length of the short packet payload data generated by IoT applications, leading to excessive waste of resources. Third, with the exponential growth of IoT devices, collisions, and network congestion would occur with a high probability due to the limited pools of the orthogonal preamble sequences and the following endless retransmission attempts. Another category is grant-free protocols-based schemes. The representative case is Aloha, which allows the terminals to transmit the data packets without any prior coordination. To alleviate the network congestion and the potential network instability issues, more advanced grant-free random access techniques have been developed, such as contention resolution diversity Aloha and enhanced spread spectrum Aloha. Another case is grant-free non-orthogonal random access. Before delivering the uplink payload data, the awakened terminals only need to transmit short non-orthogonal preambles for facilitating the detection of active terminals set at the base station. By integrating the NOMA technique and allocating unique signature patterns in the power, code, or spatial domain to different terminals, the GF-NOMA schemes can efficiently separate simultaneously served terminals from the assigned overlapped time-frequency resource blocks via successive interference cancellation or multi-user detection technology. The typical grant-free NOMA schemes can be divided into 2 categories based on channel state information acquisition. The first one is the passive case, which utilizes the periodically broadcast beacon signals to update the CSI and performs equalization at the terminals or the BS. Another one is the active case, which transmits pilot sequences to jointly estimate the active terminal set and CSI. Nevertheless, unlike terrestrial cellular systems, the wireless channels have more dynamic characteristics due to the high mobility of satellites. Aforementioned existing grant-free NOMA schemes still have their limitations. For the passive case, it is not a trivial task for the terminals to track the variation of Doppler shift precisely. For the active case, the severe Doppler effect would generally destroy the orthogonality between OFDM subcarriers. To overcome the aforementioned challenges, we introduce our proposed scheme as follows. In order to reduce the handshake delay between the terrestrial satellite links, a two-step grant-free random access is adopted. The device can transmit data to LEO satellites with the same delay Doppler resources without handshaking procedures. The payload is multiplexed in the delay Doppler domain and modulated by OTFS. The characteristics of OTFS modulation are: it utilizes the stability and sparsity of the delay Doppler domain channel to significantly reduce the number of parameters to be estimated of the time-varying channel. At the same time, it modulates the data in the delay Doppler plane and extends the data symbols to the entire time-frequency plane through a two-dimensional transform basis, making it easier to utilize the full diversity gain of the time-frequency selective channel. Due to the lack of scheduling signaling in the grant-free random access scheme, the key to its implementation lies in the design of signal processing algorithms on the satellite end, how to perform access device identification and obtain corresponding channel status information. Here, we have designed a time domain training sequence to replace the frequency domain pilots in traditional OFDM systems and the delay Doppler domain pilot in OTFS systems. Sequences are randomly generated in the time domain, such as PN sequences. Sequences are pre-assigned by LEO satellite and hold non-orthogonal for different terminals. As a feature sequence, it is used for active terminal identification and channel estimation. When processing signals at the satellite receiving end, as the received signal is a superposition of signals sent by all active devices. In the presence of propagation delay of multipath components, TSs are doomed to undergo severe intersymbol interference from the unknown payload data preceding it. In order to overcome the intersymbol interference impact on the active terminal identification and channel estimation, an effective approach is to utilize the non-intersymbol interference region of TSs, which is the tail end of TSs and thereby merely depends on the known transmit TSs. Firstly, we model the equivalent baseband channel of the satellite to ground link with multipath as a two-dimensional delayed Doppler plane impulse response. The TS received by the PTH antenna of the satellite is the superposition of signals transmitted by K potential terminal through the terrestrial satellite link, and extract the ITH length G non-ISI region. There is a convolutional relationship between the training sequence and the channel impulse response, which can be expressed as the following formula. Unlike traditional grant-free random access models, the above formula includes an unknown Doppler frequency shift matrix, and the observation matrix imposed of a time domain training sequence with a cyclic shift relationship in the Toeplitz matrix. Since the unknown of the Doppler shift matrix leads to the unknown of the observation matrix, the above model is difficult to solve directly with the compressed sensing problem. To this end, in the first stage, the Doppler matrix is approximated as the unit matrix, and in the second stage the channel parameters are purified to compensate its influence. The observation signals of all P antennas and N+1 TSs within an OTFS frame are stacked, thus forming a high-dimensional access channel matrix in the lower right corner. Furthermore, in our paper, we demonstrate the time and spatial correlation determine the common support property for the access channel matrix. The above problems can be easily solved by using many ready-made compressed sensing algorithms, such as SOMP and MMVM. Here we use the SOMP algorithm to solve the above problem. Based on the estimated access channel, we then estimate the activity of each device by determining the relationship between the energy of its channel matrix and the threshold value. Simultaneously, provide channel delay parameter estimation based on the position of the active device channel support set. Note that the estimated access channel matrix mentioned above is an erroneous result obtained by ignoring the Doppler frequency shift matrix. We further introduce the second stage to further enhance the above estimation results. Specifically, the estimated channel vectors obtained by collecting N+1 training sequences are used to provide an estimate of Doppler frequency shift. Since the error channel vector estimated based on compressed sensing estimation observation is a function of the fuzzy matrix times the estimated parameter. Therefore, joint utilization of multiple TSs can eliminate the impact fuzzy matrix and extract the Doppler shift parameters. Here, we first use Esprit algorithm to give the super-resolution estimation of Doppler parameters. The channel gain is estimated more accurately by compensating Doppler with the estimation results. Then, the delay, Doppler domain channel impulse response is reconstructed. Based on the aforementioned active terminal identification and channel estimation results, we further investigate the multi-user OTFS signal detection for the proposed grant-free NOMA-OTFS paradigm. Due to the lack of guard interval such as the cyclic prefix, the training sequence will spread into the data symbol and cause interference in the case of multipath transmission and deviation of signal arrival time of different devices. Therefore, we first preprocess the signal for interference elimination before multi-user OTFS signal detection. On one hand, eliminate the interference that the previous training sequence diffused into the data symbol. By using the estimated channel, the interference caused by the diffusion part of the training sequence is calculated and subtract. On the other hand, compensates for leakage of data symbol diffusion to the next training sequence. The leakage part is superimposed to the head to form a virtual circular convolution relationship. On this basis, we further derive the input-output relationship of multi-user OTFS signals. Since the equivalent channel matrix has strong sparsity, LSQR iterative solution can be used. To avoid direct matrix inversion, and further reduce the complexity of high-dimensional OTFS signal detection. Then, we perform simulation experiments to evaluate the efficiency of the proposed scheme. In the simulation, we assume that the system carrier frequency is 10 GHz and the satellite orbital altitude is 500 km, and calculate the corresponding Doppler frequency shift. The total number of potential devices in the coverage area of a single satellite K equals 100, active terminals K equals 10. Considering the path loss of the link, and make the link budget, the signal-to-noise ratio of the received signal is within the range of 15 to 20 dB. We consider a grant-free random access scheme using OFDM waveform without any Doppler processing as the baseline scheme, and the grant-free OTFS-based random access scheme using delay Doppler domain pilot for activity detection and channel estimation as another baseline scheme. The three figures show the activity detection error probability of different schemes, normalized mean square error of channel estimation and the variation trend of bit error rate with effective pilot overhead length. On the one hand, it can be seen that the traditional grant-free random access scheme using OFDM waveform without any Doppler processing is significantly affected by Doppler effect. On the other hand, we can see that compared with the existing pilot activity detection and channel estimation schemes in time-delay Doppler domain, the proposed two-stage scheme based on time-domain training sequence has significantly improved the performance of channel estimation and signal detection. This is because, compared with the comparison scheme, our scheme provides super-resolution estimation for Doppler parameters, the resolution is not limited by Doppler sampling grid size, and further compensation after Doppler estimation is obtained, significantly improving the performance of channel estimation. In addition, compared with the pilot activity detection and channel estimation scheme in the delay Doppler domain, the proposed scheme has higher transmission efficiency with shorter training sequences and lower cost of blank guard symbols because it fully mines the temporal and spatial correlation of the channel. Finally, we simulate the variation trends of activity detection error probability, normalized mean square error of channel estimation and bit error rate performance under different number of access devices. It can be seen that the increase in the number of access devices will lead to the rapid growth of the parameters to be estimated, which will lead to the deterioration of performance, which is obvious. However, by selecting an appropriate length of access sequence, the proposed scheme can still accommodate a wide range of changes in the number of active devices under a certain length of access sequence. As a fledgling concept, the GF NOMA-OTFS paradigm not only unveils opportunities but also poses challenges. We further discuss the challenges to be addressed and highlight the future research directions to spur more technological breakthroughs in the future. First, terrestrial and onboard constraints optimization. The IoT terminals are expected to be power constrained, which yet may result in failure to close the link considering the significant path loss. To this end, the repetition code spreading and the direct sequence spread spectrum can be integrated with the OTFS modulation to improve link SNR and enhance robustness with low transmit power. Moreover, practical satellite communication systems usually work within the saturation point of power amplifiers yet results in severe nonlinear behaviors. On the other hand, low-resolution DACs and ADCs have attracted increasing research attention to be equipped for terminal and satellite apparatus. Therefore, joint optimization of performance taking these onboard and terrestrial constraints into account is an underlying trend in the future research of multiple access paradigms. Second, interplay with other next-generation multiple access schemes. Cutting-edge NOMA paradigms, example power domain NOMA and sparse code MA, have been considered to integrate with OTFS waveform to enhance spectral efficiency and alleviate the spatial correlations caused by overloaded SDMA. It is rewarding to investigate their integration with the proposed multiple access scheme for more efficient payload data multiplexing, striking a trade-off between the spectral efficiency and transmission reliability. In addition, OTFS waveform transmission schemes rely on highly reliable signal detection algorithms to extract the full channel diversity gain. In the presence of more complicated multidimensional, Doppler, delay, spatial domains, interweaving and inter-users interference data detection and interference cancellation are worthy of further exploration. Finally, benefiting from the ultradense network topology and the conception of space-air-ground-sea integrated networks, the concept of multi-connectivity arises in LEOSATS networks. How to coordinate the intranetwork and internetwork cooperation with the multiple access scheme to facilitate the seamless integration of such multidimensional heterogeneous networks should be further investigated for service quality enhancement. Some references involved in this research work are shown here. This is end of our report. Thanks again for your attention.